Hello, this is Mrs. Scarpel, and in this video I'm going to take you through how we can simplify radicals, particularly the radicals that are considered perfect squares, or they aren't perfect squares but they involve a square root. So let's first define what a perfect square is. A perfect square is a product of two identical factors. So product means you're going to multiply. Factors are those items you're multiplying. So some examples of perfect squares would be 1, because 1 times 1 is 1, 4, because that's 2 times 2, 9 is 3 times 3, 16 is 4 times 4, 25 is 5 times 5, and so on. We also have algebraic perfect squares, so we could combine them with any of these numeric perfect squares, but also have something as basic as x squared, which is the product of x times x. You can also have multiple variables squared that are multiplied together, or you could also have variables that aren't necessarily all squares, but they all have an even number of exponents. Now, the reason we say we want them to have an even number of exponents, if I take the square root of x squared y to the 4th, z to the 6th, and I rewrite this with a rational exponent, so x squared y to the 4th, z to the 6th, and because it is the square root, it would be to the 1/2 power. And then our properties of exponents tell me that I need to apply this 1/2 power to the other exponents. So this would become x to the 2 times 1/2, y to the 4 times 1/2, and z to the 6 times 1/2. When I multiply 1/2 times each of those, I get exponents that aren't decimals or fractions anymore. 2 times 1/2 is 1, 4 times 1/2 is 2, 6 times 1/2 is 3. Keep in mind that I don't have to write an exponent of 1. I could just write x y squared z cubed. So any even numbered exponent, any even power is going to be a perfect square. So I'm going to start with just some that are just numbers. Here we have the square root of 63. First thing I'm going to do is rewrite the expression as the product of one perfect square and one non-perfect square. Well, for 63, I can write my factor pairs. 63 is the same as 1 times 63, 3 times 21, 7 times 9, and when I look at 7 times 9 now, I recognize 9 as a perfect square. So I'm going to write this as the square root of 9, the perfect square first, times the square root of 7. The square root of 9, I know, is 3. And then we have the square root of 7. Now, something I know about the square root of 7, or of 7, is that it is a prime number, and its only factors are 1 and 7. So I'm not going to be able to simplify that any further. If I could, I would break this down and repeat the process, and I'll show you that in an example coming up. Here we have the square root of 360. Whenever I see a 0 like this, I automatically think, oh, 10 times something. In this case, it's 36. Well, I know that 36 is a perfect square. So I can write this as the square root of 36 times the square root of 10. The square root of 36 is 6 times the square root of 10. Now factors of 10 are 1 and 10 and 2 and 5. I don't have any perfect squares among these four factors, so I cannot simplify the square root of 10 any further, and this is my final answer. Now let's do one that has an x squared in it, so we have the variable as well. I'm still going to rewrite the expression. I know that 54 is 9 times 6, 9 being the perfect square. So I'm going to write 9 in the first radical and 6 in the second radical. And then I'm going to look at my variable, my x, and I see that it has an even exponent. That means it is a perfect square. I'm going to place it with the 9. And the square root of 9 is 3. The square root of x squared is x times the square root of 6. 6 has the factors 1 times 6, 2 times 3. 1 is the only perfect square, but it's not going to help us break it down any further. So this is 3x times the square root of 6. If we take a look at 24x to the 5th, that would be 4 times 6, with 4 being the perfect square. Now, x to the 5th, the 5 is not an even number, but I can break down x to the 5 as a product. The largest even number before 5 is 4, so I'm going to place x to the 4 with my 4, and the extra x with my 6, because x to the 4th times x gives me x to the 5th. And this equals, I don't need that square root symbol because it is the square root. The square root of 4 is 2, x squared times the square root of 6x. Now I did mention that I was going to show you one that we could start off small and then go bigger. Let me take you to, let's try the square root of 108. 9 times 12 gives me 108. So I'm going to break this down to the square root of 9 times the square root of 12. Now the square root of 9 is 3. 12 can break down into 4 times 3, with 4 being my perfect square. So my square root of 12 I'm going to write as the square root of 4 times the square root of 3. So now I have 3 times 2 times the square root of 3. 3 is a prime number. I don't need to worry about that being broken down any further. But I can multiply 3 and 2 since they aren't under a radical. 3 times 2 is 6. Square root of 3 is my final answer for the square root of 108. So the key to simplifying radicals is to identify a perfect square factor, write that inside one radical, and write the extra factors, or I shouldn't say extra factors, but the factors that would multiply with the perfect square in a second radical. And simplify the perfect square, double check the other radical. If the other radical can be broken down, then do so. Repeat those steps.